Yeah.
But it's a pleasure to be here, and apologies for not being there live. I'm going to discuss this idea of monetizing data through forecasting and analytics task. And before you tell me it's an academic thought, we are actually developing two different platforms at Imperial College for doing that. One for healthcare and one for generic purposes. And then also there's some of these people that I mentioned at the bottom from Inesc Tech in Portugal, where they also have a prototype of a data market platform. You can find some YouTube video if you're interested. Still, I want to discuss some of the concepts that we see to monetize data through forecasting task. And the idea is really to incentivize data sharing and getting the best out of the data out there. Okay, so I have some motivating examples, some description of the platforms, zooming in on the regression market as an example, and then we will conclude. I've seen Jetro at the first row. There's some similarity with the talk I gave a few weeks ago in Glasgow, so sorry, Jetro, in advance. All right, so the context, I think today the event is a lot about energy. And I think in energy, there's a lot of forecasting problems that are very interesting. And, it's very, very interesting to hear, for instance, the previous talk about also the practicalities. But actually, many of the things that are done in forecasting for energy, it's the challenges are pretty much the same in other areas. Some areas are more advanced in certain topics, some are a bit behind, right? But whatever we do, in the future will be with some form of data and analytics when we digitalize the different sectors. So the thing is that in all these sectors, we have the same issue that data is not being shared or not as much as we would like. So many in academia and in industry these days are looking at ways to incentivize data sharing or collaboration through data. There's a typical example for energy.
Yeah. Sorry, Pierre, I don't think your slides are changing. I think we just see the title one.
Really? I'm changing the slide, guys. Oh my God, what's going on today?
Oh, no, it's moving, yeah.
Yeah, so it's when I go full screen, it doesn't like it. So I'm going to stay like this, right?
That's okay.
So, okay, so it's good. That's so strange. It's your teams. It's not me. All right, but so I have this motivating example about electricity markets, which I think is very nice because it builds on our experience with 10, 15, 20 years of interaction with industry. So you have all these wind farms or renewable energy assets participating in the electricity market. They have to place offers in advance, which makes that you need forecast, right? And then the revenue is directly affected by forecast accuracy, right? So you believe everybody has an interest in improving the forecast. We know this can be done through information sharing. There's been many papers showing that if one shares local measurements, weather forecast, etc., you can improve the forecast quality. So you believe everybody would be better off by sharing information. But whenever you discuss with energy companies, traders, utilities, whatever, they are not very keen on sharing their data. There's many reasons for that. I don't think we're here to discuss or point fingers. I mean, it's totally fair, but we have to find ways to get people to share data for the common good. Because at the end of the day, if data is shared, it's going to increase social welfare. Everybody could actually get something out of it. The problem is to design the right framework. So here in this example that you see here with these 3 wind farms going into the electricity market, for instance, if we could design some kind of agreement between this wind farm for distributed computation or data sharing. So let's say wind farm B is in the middle and trying to improve forecast. Maybe this wind farm could get access to data of wind farm A through distributed computation, directly to data from wind farm C versus payment. Eventually, wind farm B could get better forecast, better revenues from the market, and wind farm A and C would get the revenue from the market, and on top of that, revenues from this database collaboration. So we can just design different type of business models like that, where we would see somehow that it should be the case. Everybody's better off if we design the framework properly. So I want to go through a few business models or ideas to do that. And then you will see some of the ideas are actually already picking up for different reasons, and some of the ideas will require a bit more work. So typically, it's something that would happen in the platform economy in the future. I mean, this is something that we see more and more for different type of application that are most often not data related. But I think also for data, it will make sense that we have this kind of platform economy for data sharing. And these are three different business models that we may think of. So in all cases here, you have something that I call a central agent. It's someone or a firm that want to solve an analytics task. So it can be regression for forecasting, it can be classification also. And this agent realizes the task could be better solved. You would get a better forecast quality, for instance, or classification accuracy by using data of others. So then these support agents, they are those who own this extra data that the central agent would like to have access to. And we want to find a way for this to work, right? So on the very left, we have this idea of collaborative analytics. You can put in there federated learning, you can put distributed learning in other type of version. You know, we can always find a way to split a learning problem, an optimization problem when you fit a regression, for instance, so that we have some kind of iterative process between the central agent and support agent. The actual data is never shared through the iteration process. You know, we hope the data is not revealed. You may need a privacy preserving layer there, but that would be the way somehow for the central agent to profit of the data of others without having the actual private data being shared, right? So this model actually exists. There's a few papers out there written by different people. It's heavy to implement in terms of computational cost architecture, but it's feasible. In the middle, you have something that others have argued for, is the idea of just monetizing data, right? You have a data market and you say, okay, we need a platform so that people say, I want to buy data. Some other people say, I have data that can sell. And then you have some kind of allocation and pricing mechanism. So there the problem is that data in general, and for so many applications, is a very weird commodity. It's difficult to price. The way it is priced may be a function of so many things that are not really classical aspects we think of in economics. So for instance, with data, you know, access to data may not be exclusive, so it affects a lot the pricing. The timeliness of the data is very important. So actually, if you buy the data in real time, 5 hours after, 20 days after, it doesn't have the same value. Also, data being shared, you can never be sure if it's a real deal. You know, there might be a measurement quality issues, someone might be cheating. So how do we accommodate all these things together? So it's a quite difficult setup. And then on the right, I mentioned this thing, which is analytics markets, and that's what I'm going to zoom in afterwards, is because if we specify on this platform a very specific task, so I want to you know, fit a regression model for this specific location, for this specific periods, etc. Actually, it's much easier to price the data and to have something that makes sense. So my opinion is that it's an easier way to implement this idea of data markets, but somehow all these business models are legit and could be used for different type of areas. So for instance, in healthcare, as of today, they much prefer the business model on the left. If you think of, let's say, tourism, business analytics, or think of Bloomberg, for instance, their business model is the one in the middle. And I think there are many people developing the business model that's on the right, okay? But there's also something for which I think forecasters have been quite early in the game. It's this idea of prediction markets. So there's also quite a few ideas out there where people say, okay, you know what, if you want to better solve a task, you can always turn it into a prediction problem. You post the task online, and then you get people to bet. You know, they formulate their forecast, they make a bet that becomes a wager, and then we have some way to reward the people or the agent, the bots that made a bet. Hopefully, you get a better forecast, and everybody who contributed gets a payment if they help, or they get nothing if their prediction were crap, right? So we have a few examples of that, and this has been there for quite a long time. So we have many ideas out there to actually incentivize collaboration based on distributed data. And now we have to find ways somehow to bring that to many applications. And energy is one of the, I think, of the big application areas in the future. So this, actually, I gave a talk at the ISF last year on this topic. We just had a paper published in the IGF with this guy, Raja, who was a PhD student at TU Delft. And for instance, we proposed one approach where we were talking about forecast for energy in the previous talk. If I make a forecast for energy prices or renewable energy production for some assets, I could also post a task online and ask people if they can do better than me or they can improve my forecast. And so what we describe in this paper is that there are actually ways to do that, to post a task and get other people to bet somehow. They propose an alternative forecast, they make a bet, and then we have some mechanisms so that we fuse the different forecasts, promise that we're going to get a better forecast out of it, and also we have a way to give a payment somehow to all the contributors, and we can prove that it's efficient, it's fair, etc., etc. But now I want to zoom in on a specific example. I'm going to try to do that in like 5-10 minutes max. It's this idea of regression markets. There's a paper, open access, that was published not so long ago, so you can just get the paper if you want to see the detail. And then here I present it in a very simplified setup, but this can be used in more complicated setups in the future. So you're all data scientists, I guess, in the room. So I'm going to assume that you know how to do your regression. Imagine that you have a central agent. I described what a central agent was before. So we're going to call it forecaster. This central agent is doing some form of regression for predicting renewables at a given site, right? So to do that, this forecaster has a set of own features. So that can be weather forecast, that can be past measurements, that can be distributed measurements around the wind farm, etc., etc. So normally what the forecaster is going to do is fit a regression model. So assuming you have this bunch of features as input and you have this regression model here in the middle. When you fit the regression model, you get the set of estimated parameters. So that's your regression coefficient. Here they're written as beta hat. And then you have the value of the loss function when you fit your model. So it can be, you use a convex loss function. It can be a quadratic loss. So you relate it to some kind of mean squared error. It can be a pinball loss if you want to predict a quantile. But whatever loss you choose, you're going to have the value of the objective function when you fitted your parameters, okay? So now this is only using the data of this central agent. But based on what I was saying, this agent could go to an analytics platform, post a task saying, I want to do some kind of regression for this period, for this response variable, and I'm willing to pay, let's say €1 per % improvement in a mean squared error loss function and per data point provided, okay? So what happens then is that you have some agents that will go to the platform and bring additional features. So here, there's just an example with two features, Z1 and Z2, and you have two agents, good data and useful features that bring these two features, okay? So we have also then an overall set of features that is the features of the central agent, forecaster, plus these two individual features brought in by the others. And we can do the same as before. We can refit a regression model, which is the same as we had the previous slide, plus the two extra features. Everything is linear and easy here. We could do it in a more general setup. When we fit this model, we have a new set of coefficients. So for the extra features too, right? And it may have affected the coefficient for the other features. And we also have a new objective function value at the optimum when we estimated the coefficient. If the two features are valuable, normally the objective function value is going to be lower than the objective function value we had before without these two features, right? So somehow the value brought in by these two features would be the difference between the two objective function value when estimated the parameters, all right? So that's kind of the cooperative value creation in the game somehow. So then we need a mechanism to define some kind of revenues and payments because we want to make it a market, right? And there we can actually directly apply the idea I mentioned before. The central agent came to the platform with a willingness to pay, which is a function of the improvement in the loss function, right? So let's say mean squared error, and the quantity of data being provided. So you see this formula here at the top, pi c equal something. So we have this willingness to pay, multiplied by the improvement in the loss function, multiplied by big T, which is the quantity of data being provided. So that's the payment of forecaster for the help of the others, right? If there's no improvement in the loss function, the payment is 0. You can see because the delta loss is going to be 0. And now for sharing this payment, so that becomes a revenue for the two agents that provided features, we can use tools from interpretable machine learning. So think of it of a SHAP, additive explanation. You can actually tell, the improvement in the loss function when fitting the model. 40% comes from the first feature, 60% comes from the other feature, right? So the payment made by the central agent forecaster and then split it following this allocation policy. And this is how the money is shared. So if one of the features bring 90% of the improvement, the owner of the feature gets 90% of the payment, and then the other one gets the rest here, okay? If we do that, it has actually a lot of nice market property. I'm not going to go into all the details, but it's something that is very important when you design a market, when you look at mechanism design. If you don't get proper market properties, then it's not going to work in practice, right? So now we have a market so that we can have different agents providing features in a regression framework. The thing is that whatever I was telling about was about batch learning. So, when you fit a model to the data, and we all know that forecasting is not about that, right? Is that you have to use the model out of sample after for forecasting. But what we showed in the paper is that actually all the concept I showed you, you can use it in sample, so when you learn, but you can also use it out of sample. So when you do genuine forecasting, you can also collect the errors, actually see how much the different features have contributed to improve the forecast accuracy, and you can just pay agent accordingly. Okay, I'm not going to go into the detail with that. So I have a quick application to share with you. We had a few case studies. This is the nicest one because the data is open, so people could reproduce the example. It's in South Carolina with 9 wind farms. You have the location there. And we looked at 1 hour ahead forecasting, assuming you have an electricity market, which is with short lead time like this, right? So like you would have, for instance, in Australia and other places also, you have electricity markets that are with shorter lead times. So you can see at the bottom, the kind of a model that we use for forecasting is an autoregressive model with exogenous input. So all the agents here, which is 1 wind farm each, use their local data, but also will buy data from the other agents. So that come in the last term of the regression model here, which is the features of the others, right? So what happens if we do that? In this case here, we use online learning and we use a quantile regression setup because most often when you participate in electricity market, it's a quantile you want to predict, not the conditional expectation. And then the agents declare a willingness to pay in sample, so for learning, and a willingness to pay out of sample, so for genuine forecast quality, okay? Here, the 2 plots are for cumulative payments made by A6, so it's one of the agents, towards the other agents. On the left, it's for the learning part, and on the right is for the genuine forecasting part. Already, you can see, based on the lines and the legend, there's only 4 agents out there. Because through the feature selection, it was seen that some of the agents don't bring value to improve the forecast quality for agent A6. So they're just out of the game. They're not part of the market at all, okay? But for the 4 agents that were selected, these are their cumulative revenues through time as the data is used through the regression market. The slope is different. That means that the data of the various agents is more or less valuable. If you were to see what happens after 7 years, 6-7 years of data there was there, you can have this kind of bar plots. So on the x-axis, you have the name of the agent. So it's A1 to A9. And the size of the bar is for their overall revenue, right? And then what compose these bars is who pays, right, for getting access to this data. So if you focus on the left plot, which is for learning, again, on the very left bar, it is for agent A1, and the overall size of the bar is how much A1 gets as a revenue over the 6-7 years paid by the others. And so it's around $25,000, right? But out of this $25,000, the brown part of the bar is what A2 paid to A1, the next green, military green, is what A3 paid to A1. The more, let's say, greenish green afterwards, that's very small, is what A4 paid to A1, etc., etc. So what we see from these two plots, again, learning on the left, out of sample, forecasting on the right, is that the value of the data of the different agents vary a lot overall, because when the bar is very large, that means they have very valuable data for others. And when the bars are very small, that means their data is not very valuable for others, right? And also, the agents pay very different amounts for access to data of each other, right? So overall, you know, that's what you expect of a free market, you could say here, is that we endogenously reveal the value of the data of the different agents for each other. So here it's a small market with 9 agents, but if you were making it bigger, we would see even more interesting stuff. At the end of the day here, we can see that an agent like A4 with a very small bar, you know, the value per data point produced over the 6-7 years period is of only $0.4, right? But another agent like A8 that has these very big bars, the value of for each data point being collected and shared is 8 times more, right? So it's interesting in terms of revenue stream and future business models. It seems like in an energy market, the value of the data collected by the different agents can actually vary a lot, right? So you may want to be a bit smart if you think of selling your data, right? Good. But in terms of conclusion, I think there's a lot of room for this collaborative and market-based analytics in the future. In healthcare, it has already picked up. There's a lot of interesting things going on, you know, companies, business models, investment, etc. I think it will happen in energy for sure, and in some other applications. The thing is that here I was showing you a very simple example, but there are many complexities that require more methodological development in terms of statistical and machine learning. And then we also have to be very smart in the way we design the use cases and business models. Some people are a bit obsessed with privacy these days. So what would be interesting is to look actually at how privacy can be accounted for in this framework. And then there's also some aspects with competition, because here, for instance, you could say, well, some of the agents will just not want to participate in this data market because they don't want to share data. If someone else performs better in the electricity market thanks to my data, maybe I'm going to be affected myself, right? So maybe I just don't want to share data by design. So, for instance, for this specific example, a clear path for the future is to actually have a joint data and electricity market, because then you could consider the two together. And something we proposed actually quite many years ago, and I think it would make sense in the future to think of that. Maybe in the UK, maybe somewhere else, I don't know. But thanks a lot for your attention, and I'm happy to take some questions if you want.
Any questions in the room or online? Yeah, go on.
I don't know. Can you
Just speak right to the loudly. The mics are in the ceiling, so they should be able to.
Oh, thank you, Pierre, for the presentation. A quick question about, I mean, as all of us, we know when we have predictors, it is likely that we need also the forecast of the predictors to be useful to forecast the future. So I was wondering whether you refer to data, whether that includes also the forecast, or it is just the actual values of the feature or the predictor, and then whether the loss function would take that into account or not.
Yeah, so thanks a lot for the question. So here it's directly the feature that's used as input in this regression model, right? So if some of the features are actually forecast for something, it still works. It doesn't have to just be measurements, right? So I can give you a specific case because that's what we did with this guy, Ricardo, I mentioned, and Carla in this EU project. If you do it, for instance, for renewable energy forecasting, we get forecasts for weather variables, right? And we use this forecast for weather variables as features, input features in this regression market. And you can do that too. It doesn't have to be measurement. Actually, what's interesting there is that you would have an interest in improving your forecast that you provide as input here, because most likely the better your forecast is, for instance, for wind speed, the better it would help to improve the wind power forecasting model. So the money you would get or your revenue would increase if you increase your input forecast for this regression market, right? So I think it's actually an interesting case that it can be both. It can be measurements and forecast as input features.
Hi, thanks, Pierre. That's really good. I might have got this wrong, but is there a chance here you can kind of like pay for the same value that each agent's bringing, though? You know, if you sort of have someone who brings temperature forecasts and one brings wind chill, they're obviously really confounded or could correlate with each other.
Yeah.
And is
No,
that paying for it twice, are you? Or?
No, so you would not pay twice. The problem, so you would somehow capture the value of this information only once through the fitting of your regression model. The problem is the way you're going to pay the people with their input feature is not going to be efficient and fair, right? So some might be overpaid and the other one underpaid somehow for the information they bring. So what has been proposed by some colleagues at MIT, for instance, is to find a way to calculate these Shapley values for the interpretable machine learning that is robust to the problem of correlation. Some other people have been looking at alternative ideas. We're also looking at some ideas for that. But I agree with you. It's one of the big issues with this idea is that if all the features are independent, it works like a charm. But obviously, if the features are correlated, which is the reality in many applications, then you have to be a bit careful with what you do.
It seems like you might have an issue with winner's curse in your auction markets, right? Because you have a lot of uncertainty about whether a model is actually better than one model is actually better than another model, and so the likelihood for features seems really high.
Yeah. So this is also something we've been looking into. It's more about the business model here, right? Because you have to decide who is responsible for choosing the model. You could say either the central agent goes to the platform and choose from a catalog, that's the model I want. Please run this thing for this specific model, right? So the responsibility is on the central agent when going to the platform. But another business model could be to say that when the central agent goes to the platform, the central agent asks the platform to also find the best model to extract the juice somehow from all the features being provided, right? And there you could start discussing, is the platform doing the best job, right? But the first business model is actually quite interesting. And that's what these guys in MIT, they wrote when they first wrote a paper on this topic. They say, let's make it the responsibility of the central agent. From the moment the central agent say, this is the model I want, you say, given the class of model you propose, I did my best as a platform, and that's it, right?
Go on to the last question. Thank you very much for the presentation. So I was wondering if you'd consider this challenge, which is that whilst I can well see that it's possible to estimate how much each feature decreases your forecast error, so your mean absolute error, it's often very difficult to go from that increase in forecast skill to an increase in revenue for the business. So system operators, for example, it's still a room full of humans that are making sometimes hard to understand decisions. And I was just wondering if you considered how that would play into this market and how you price the features.
Yes. So it's a general question in economics, right? In any kind of economic system, you have the same as what I said here. You assume an agent comes with a willingness to pay, right? So you have a concept of utility for the buyer. And often in economics, we believe that this agent can do his or her job to estimate that, right? And then go to the market and use this value to participate. I agree with you that in many applications here, it's very difficult based on data to link forecast quality and value, right? And that's why I was saying in some cases, like for energy, that would require to blend the two markets together for energy and data, because then you could just reveal it directly when combining the two, right? You would reveal what the data is worth for all the agents because you clear at the same time the data and the energy market. So I think there's some kind of application areas like that where you could just, combine things together so that it becomes, endogenous, right? It would just happen by itself. but for the most general case, I mean, we're gonna have to do like classical economic theory. We have to assume that is the job of this agent to do that, right? To estimate through simulation, sensitivity analysis, what is their willingness to pay to improve forecast accuracy for whatever application they have in mind.
Thank you.
Thanks.
Very much, yeah.
Sorry once again for not being there. And I'm very happy Ivan and Jetro were saying they might be looking for people to host. I'm very happy to host you in London sometime in the future, whenever is relevant, right? So thanks a lot.
Thanks, yeah.